Hello, this is the notes for calculus class. We're starting chapter 4. What we just finished in chapter 3 is really, the whole thing was really just about the definition of a derivative. And that was that long drawn out limit as h approaches 0 of f of x plus h minus f of x all over h. So you had to plug in a bunch of stuff, simplify things. And it defined what a derivative is, and that's the definition. It is the limit of a slope, but it's the limit as the slope of those 2 points come together. So it became the slope of the tangent line. That's the derivative. Slope of the tangent line is also the instantaneous rate of change, like it says right here in the first, first bullet. All right, so that's the key thing. We just had to define what it is so it makes sense. When we talk about a derivative, we are talking about slope of the tangent line. We are talking about that instantaneous rate of change at a certain x value. And we just had the definition. That's all we really had. So this way you're going to be frustrated with me, but we're going to find a really quick way to do it instead of doing that whole long drawn-out process. But some notation. Okay, we've seen this. F prime of x, very, very common. You might even see y prime like this. You don't see that very often, but it exists. You will also see this quite a bit. This dy over dx. Like it says right here, how you read that is the derivative of function y with respect to x. So instead of seeing this, this is what you should be writing or seeing. The derivative of y with respect to x. It's a bad x, but those are the most common ones. Sometimes you'll see this. Not very often do you see this last one, but it's the derivative with respect to x of function f is how that would appears. So the first two, most common ones. This is our notation. All right, so there are a couple of rules. We're going to find the derivative much, much quicker instead of applying the definition. So first one, the constant rule. If your function is a constant, something like f of x equals 7. Okay, that is a horizontal line. Slope of the tangent line to a horizontal line is 0. The derivative is slope of the tangent line. So if your function is a constant number, the derivative is going to be 0, always. The next one is the power rule, and this is the one that we apply most often. This is the one that you're not going to like me because it's so quick. But what it says, if you have a function f of x equals the variable to a power. All right, doesn't matter if it's an integer, fraction, positive, negative. Like it says right here, that exponent is a real number, which is positives and negatives and decimals and fractions and all that other business. So f of x equals x to the power of n. The derivative is going to be, you bring that exponent of n out in front and then decrease the exponent by 1. So as a quick example, if f of x was x cubed, the derivative of this function would be bring the exponent of 3 out in front times x, decrease the power by 1. So 3 minus 1 is 2. There is your derivative. 3x squared is the derivative of x cubed. It's called the power rule. It's the quick and easy way to do the derivative. Instead of going through plugging in x plus h, cubing it, subtracting x cubed, and then simplifying that limit, taking the limit as h approaches 0, we got the power rule. And it works for these polynomials, x to the power of n. All right, a little bit of a combination. Well, actually, no, it's not a combination, but constant times a function. So what we're looking at is where we got f of x equals something like 3x to the 4th. So there's that constant of 3 out in front. What this says is, here's our generic function, k is the constant times another function g. The derivative, you just leave that value of k out in front and then take the derivative of that function g. So for this one, f prime of x would equal, keep that 3 out there in front, times, now we're taking the derivative of x to the 4th. So use the power rule just like we did above. The exponent of 4 moves out in front, as a multiplier, times x, decrease the power of the variable by 1. So 3 times 4 is 12x cubed. That would be the derivative of 3x to the 4th. So when there's a constant out in front, just keep it out in front. It just becomes another multiplier. Okay, the last one here, sum or difference. Basically, if your function has terms, you're adding and subtracting different powers, so like a normal looking quadratic, x squared plus 5x plus 7, you just take the derivative of each term. Okay, so as a quick example, f of x equals x squared plus, I don't remember what I said, 5x plus 7 maybe. The derivative of that, f prime, you just go term by term. The derivative of x squared, using the power rule, is 2, exponent comes out in front, decrease the exponent by 1. So that becomes x to the first, we can just write it as x. Plus, now we got this constant, so that stays there. 5x, technically that is x to the first power. So we're going to multiply it by 1 times x, decrease that power by 1, so it becomes x to the 0. Plus 7, the derivative of a constant up here is just 0. So f prime of x is 2x. 5 times 1, x to the 0 is just 1, so we got plus 5. Plus 0, we don't need that. That would be our derivative, 2x plus 5. Okay. So now, a couple more examples. F of x is a constant. We want to find its derivative. Derivative of a constant is 0. Doesn't matter what it is. All I'm talking about here is just the change in notation. You're given y equals an equation, so we're taking the derivative of it. So dy over dx. In this first example, we were given f of x, so we're going to use the notation f prime. When you're given y and you're asked to find the derivative of it, dy over dx. It's the derivative of this equation, but it's a constant, so it's still 0. All right. For the second row, again, we're given y, so it's dy over dx, the change in y over the change in x. Power rule. Exponent comes out in front, decrease the exponent by 1. So it's 4x to the third. For this one, f prime of x. What we're looking at here is really x to the first. So you got 1 times x to the 0. X to the 0 is just 1. Okay. Again, think about the definition of derivative. It's the slope of the tangent line. The slope of this line right here is 1. Okay. When you're taking a tangent to a line, it is the line. So the slope of this line is 1. The slope of the tangent line is 1. That means the derivative is 1. All right. For the next one, to find f prime, we got the square root of x. Now, the square root is an exponent. So with this, what we want to do is rewrite our function. The square root is to the 1/2 power. Okay, this is where it gets a little bit tedious. It's not all super quick and fancy like this x to the 4th example on the left. You got to be a little bit careful once you start dealing with exponents that aren't integers. And we're going to get into some negative exponents also. But the rule is the same. That exponent, bring it out in front as a multiplier, times x, decrease the power of the variable by 1. So 1/2 minus 1 is a negative 1/2. So now what we're looking at is 1/2 times, when you have a negative exponent, that goes 1 over the base to the positive power. Okay, x to the 1/2 there is, bring the page up a little bit if I can. X to the 1/2 is a square root. So when we multiply these fractions, we got 1 over 2 square root x. That is f prime. All right. That x to the 1/2 was a square root. When we multiply fractions, we go straight across. So numerator is 1, then we got 2 times the square root of x for the denominator. All right. Just a couple more quick examples here. Not much is different here, but dy over dx equals 4 times exponent out in front, decrease the exponent by 1. So that gives us a 20x to the 4th. And try these ones on your own. I'll talk about these in class. That is all.